This is problem 613. It's on page 344. There's a general problem statement for all of these problems, and that's to find the centroid of the area and also the second moment of the area. So we use the first moment to find the centroid. We want the second moment of area about an axis through the centroid. Now in this case, because of the way it's oriented, I'm going to choose a horizontal axis, but they didn't make that plainly clear. But that's what I'm going to choose. There would be a different moment of inertia if I chose a vertical axis going through the centroid. But anyway, let's see how the areas are broken down. You can break down this shape many different ways, but essentially all of it consists of rectangles. So I'm going to highlight the rectangles as I go. So I'm using a spreadsheet to calculate it just to make it easiest. And to calculate the centroid, I need the amount of area and the height of that area away from some axis. Well, the axis I'm going to choose to be consistent is this lower line here. So you notice a baseline dimensioned from that line, and so that'll be my reference axis. So the first area that I'm dealing with here in the first row is actually this area up here at the top. It's just that area. That area, let's see, there's a 5 millimeter typical thickness in this whole section. So 5 millimeters times 10, well, that's 50. That's where this number comes from. And then YI, that's the location of the centroid from the axis that you've chosen. Like I said, I chose this axis down here. So from here up to the top is 55 millimeters. Then I need to take away 2.5 millimeters to get to the center, or the centroid, of that little bit of area. So that's down by half of 2.5, or half of 5 millimeters, which is 2.5 millimeters. So 52.5 millimeters is the distance from the line down here at the bottom of the shape up to the centroid of area 1. Now then the spreadsheet goes ahead and calculates the product of those two. We'll worry about the rest of this in just a minute. Let's go ahead and consider the other shapes. So what are the other areas? Well, let's jump down to 5 and 6. Those are pretty easy to see because look, they're an area of 50. So all I'm doing here is dealing with this foot and this foot. Okay, that's it. So all I'm doing is taking that area times the height from the axis of reference down at the bottom up to the centroid of the area. Well, that's only 2.5 millimeters up, so you see where these two numbers come from. And of course the product of 50 times 2.5 is 125, so there we have it. What about these others? Well, I have to remember them, but I think we can remember them pretty easily, or figure them out pretty easily. Notice I've already taken into account this area and this area. I've got a 5 millimeter thickness and a 45 millimeter height. Now what I like to do, rather than figuring that out in my head or using a calculator, is to realize that I've got a really good calculator sitting right here in Excel. And look at that, 45 times 5. Makes it easy to see where I got some of these numbers from. That way if I finish and somehow know I've got the wrong answer, I can go back and find my mistake easily. So use Excel as a calculator. It's a great calculator, it works really well. So 45 times 5, that must be this upright, and what I'll do is just rearrange my rectangle so you can see what area I'm talking about. So that area is this row where we've got 45 times 5. Okay. So the center of that area is just halfway up, half of 55. You notice I typed in 27.5. I probably should have typed in 55 over 2, but that's fine. So notice that's not the distance from the bottom of the area to the centroid, it's the distance from the reference up to the centroid of that area. What about the other two? Well, 5 times 20, I don't remember which leg that is. We've got 5 times 20 and 5 times 25. We can tell by the height. See the height here at 27.5, that's halfway up. Where would that be? Well, that must be this area. Let's see. Rearrange our rectangle a little bit. That must be that area right there, okay? Because that area, certainly its centroid, lies at, let's see, 30 minus 2.5. So 30 minus 2.5 would be 27.5. That's where this number comes from. So this row, or part 3, is that part I've got highlighted. And then finally, part 4 must be this other leg over here. Remember, I've already taken into account this part down here, I've already taken into account that whole foot. So I don't need to double count it. It would be a mistake to double count it. So that's 25 high by 5 wide. 5 times 25 is 125. And the center of that is up at, well, let's see, we need 5 plus half of 25. Well, half of 25 is what, 12 and a half? So plus 5 is 17 and a half. So you notice I did some of the math in my head and typed in numbers in the spreadsheet. The more you don't do what I just did, the more you type in, like here I should have probably typed 5 plus 15, oh no, that was 25, see I almost made a mistake there, 25 over 2. It's the same thing, right, 17 and a half. But anyway, there it is. So then the spreadsheet goes ahead and calculates the sum of the AIYIs. In other words, the moment of all those individual areas from this axis. And then it calculates the total area just by adding these up. And then, of course, with these two cells, you can take the ratio, and that tells you where the centroid of the whole shape is located. So it's just an area balance is all it really is. Imagining an axis, you know, a mirror axis at the bottom of these, you know, underneath these feet. So y is at 23. Well, where's 23? Well, let's see. 30 is up here. There's 25. So 23 is down, you know, here somewhere. I don't know exactly where. It's somewhere in there. It doesn't matter too much. But that's where the centroid is located, at least from the bottom. We don't know left and right because we're not dealing with that direction. We're just dealing with, you know, up and down the height. The vertical dimensions are all we're dealing with. And notice that the 2 feet at the bottom, for example, it doesn't matter where those feet are in terms of left and right. What matters is how far they are up and down from our reference axis. You'll notice that the effective AIYI for these areas, for example, this area, and I don't know which foot is which row, it doesn't make any difference. They're the same, right? Because, as I said, the left-right position doesn't matter. But I do know that the 2 feet at the bottom are rows 5 and 6, whereas this, although it has the same area, that's the one at the top because look how much higher it is. So it contributes more area moment, okay, because it's farther from the axis that we're taking the moment about. So now let's move on to cell E. Well, this is the area we're talking about. We're on row 1. What is the moment of inertia, the second moment of area for this area? Now here you have to be careful because here what we're doing is we're calculating the moment of inertia from some tables, page 690 and 691. If you haven't marked them, you should go mark them now, because this is what tells you, or this is where you've got a collection of formulas to tell you how to calculate the area moment of inertia, or the second area moment. Be careful with this though, because you always get the area moment of inertia through the centroid axis of that area. So this 104.17, we'll see where that comes from in a second, it's through the centroid of this little bitty area. But I don't care about that so much. What I want is the moment of inertia of this area about the centroidal axis of the entire shape. So, by the way, where do we get that 104.166? Well, you might notice that it's 1/12 bh cubed. So what is b? B is the base. H is the height. So you notice we've got the base 10 millimeters and then height 5 millimeters cubed divided by 12. That's just an equation you'll probably have memorized before long. It's really just the equation of the moment of inertia through the centroid of a rectangle for that rectangle. Now obviously if I had an axis running vertically through it, I'd get a different thing because the height would be different. The height in that case would be 10 and the width would be 5. But because I'm interested in an axis running horizontally, since that's what I'm doing with the whole overall shape, well then the width, or the base, is 10 and the height is 5 millimeters. Okay, so then what? Well, the next part here calculates how far it is from the centroid, that's capital Y, okay, so that comes from here, from the centroid to the center of this area. Now notice I've already got the center of that area. It's right there, right? I've already told the spreadsheet what it is. So we can easily take the difference between cell C9 and C2, and that then is the distance between the centroid of that upper rectangle and the centroid of the overall shape. And then I can calculate that area times that distance squared, so that I can then calculate the moment of inertia of this area about the centroidal axis of the whole shape using the parallel axis theorem. That's what cell H1 is describing to you, is that we're using this to add the second moment of area of the shape through its centroid to that area times the distance squared to another axis. We're just moving the axis. And of course we end up with a much higher moment of inertia. Now, one way you can think about this to help your intuition is imagine an axis running through the centroid of just this little red shape here. And you've got it on a stick and you can spin it. Okay? As you spin it, it's pretty easy to spin. Now imagine moving that axis much farther down to the centroid of the overall shape, and somehow still connecting it and trying to spin it now about that same, or about a horizontal axis. That'll be much harder, and that's really what this number is getting at, is how hard it is to spin that area. That's a good intuitive argument, maybe not a good mathematical argument, maybe not exactly precise, but it helps me remember and understand what I'm doing here. So the same thing is being done for all the other shapes. Notice we just have a bunch of rectangles. Calculating their moment of inertia is nothing more than deciding how tall each rectangle is and how wide. And of course the next rectangle in row 2 is this one. It's 45 tall and 5 wide. That's why we get such a large number here. The base is 5, the height is 45, so 45 cubed ends up being pretty large. But then the centroid of this area is not very far in the vertical direction from the centroid of the overall shape. So you notice that D, the distance here, is much smaller than it was for the upper area before for part 1. And so AD squared is fairly small by comparison, and we get a similar moment of inertia for this entire large shape about the centroid as we got for this little bitty area, because it's far from the centroid. See, so these two numbers are pretty close together. They're both on the order of 42,000 or so. And so the reason is because there's so much more axis offset in the smaller area, very little axis offset in the larger area, but the larger area has area distributed away from its centroid much more so than the smaller area has. So that's how all of this works. If you go through and you look at it, it should all make sense. I have posted this spreadsheet for you. You can download it and look at it if you like. I won't have this area highlighting any of it, but hopefully this will help you in understanding. Now, at the end, since I want the moment of inertia for the whole shape through the centroid, notice that all of these have used the parallel axis theorem in order to move the effective axis of each of the individual areas to where they are all through the centroidal axis of the whole shape. And so to get the area moment of inertia, the second area moment of the whole shape, you just add them all up together. And so that's what's being done here. So this is a nice spreadsheet. I highly recommend you use it. I have posted it for you. Just add a tab and copy one of the tabs to start using it. You can look back at these as examples.